What happens when a star dies? Does it simply fade away into the darkness of space? Or does it go out with the most violent, breathtaking explosion the universe has ever seen? Welcome to the story of supernovas, cosmic detonations so powerful they can outshine entire galaxies and forge the elements that make up you, me, and everything we know. This is the explosive truth behind the death and rebirth of stars. Let's start with the basics. A supernova is the dramatic death of a star, but not just any star. These explosions are the final, fatal act of massive stars, those with at least 8 times the mass of our Sun. But not all supernovas are created equal. There are 2 main types. A Type 1 supernova is usually caused by a white dwarf stealing too much mass from a companion star until it goes boom. And a Type 2 supernova occurs when a massive star runs out of fuel and collapses. Think of it like a cosmic pressure cooker. The star burns fuel, mainly hydrogen, fusing atoms together to release energy. This energy pushes outward, balancing the crushing force of gravity. But once the fuel runs out, gravity wins. In a fraction of a second, the star's core collapses in on itself. Temperatures soar to billions of degrees. Then, bang! An explosion tears through the star, ejecting material into space at thousands of kilometers per second. This is a supernova. Let's rewind. To understand how a supernova forms, we need to look at a star's life. Stars are born in clouds of gas and dust, called nebulae. Over millions of years, gravity pulls this material together into a dense ball. When the core gets hot enough, nuclear fusion ignites, and a star is born. For billions of years, the star fuses hydrogen into helium, releasing energy. But eventually it runs out of hydrogen. Heavier elements begin to fuse, helium into carbon, carbon into oxygen, and so on, until iron forms. Here's the twist. Iron doesn't produce energy when it fuses. Instead, it consumes energy. And when fusion stops, the core collapses. In less than a second, a star that's been burning for millions of years implodes. Then, the rebound. The outer layers smash into the collapsing core, creating an explosion so bright it can be seen from across galaxies. There are several types of supernova, but let's break down the big ones. Type 1a. These happen in binary systems, where 2 stars orbit each other. A white dwarf pulls matter from its companion until it reaches a tipping point and explodes. These explosions are incredibly uniform. So uniform, in fact, that scientists use them as standard candles to measure the size of the universe. Type 2, these are the core collapse supernovas we've been talking about, the death throes of massive stars. But there's more. Scientists have discovered variations. Type 1b and 1c are stripped-down versions of Type 2, where the star has lost its hydrogen or helium layers before the explosion. Each type tells us something about the star that exploded and the environment it died in. Here's something truly mind-blowing. Everything around you, your phone, your blood, the air you breathe, contains elements that were forged in the hearts of stars and released in supernova explosions. Stars are fusion factories, but it's the supernova that creates the really heavy stuff: gold, uranium, platinum. These elements didn't just appear, they were born in a cosmic blast. Carl Sagan once said, "We are made of star stuff." And it's literally true. When a supernova explodes, it seeds the universe with the raw materials for planets, moons, and life. Without supernovas, there would be no Earth, no oceans, no humans. Throughout human history, people have witnessed supernovas and recorded them. In the year 1054, Chinese astronomers documented a guest star that shone in the sky for weeks. It was a supernova, and today we call its remains the Crab Nebula. In 1604, Johannes Kepler observed another bright new star. This was the last supernova seen with the naked eye in our galaxy. These ancient observers didn't know they were watching the death of a star, but they knew it was something extraordinary. Today, we use space telescopes like Hubble and Chandra to capture supernovas in stunning detail. Despite all we know, supernovas still hold mysteries. In 1987, a supernova called SN 1987A exploded in a nearby galaxy, the closest observed in over 400 years. It gave scientists a goldmine of data. More recently, we've detected superluminous supernovas, 10 to 100 times brighter than a typical explosion. Some even produce powerful gamma-ray bursts. And there's more. A rare type of explosion called a pair instability supernova might happen when extremely massive stars, over 100 times the Sun's mass, blow themselves completely apart. No remnant, no black hole, just gone. And then there are failed supernovas where a star collapses silently into a black hole. No explosion at all. We're still learning what stars are capable of. Supernovas aren't just fireworks for the cosmos. They're essential to how the universe works. Without them, galaxies wouldn't evolve, planets wouldn't form, life wouldn't exist, and scientifically, they're critical. Type 1a supernovas helped us discover dark energy, the mysterious force accelerating the expansion of the universe. They're cosmic beacons, chemical factories, and agents of change. They are destruction and creation, wrapped into one. Here's the million-dollar question. Could we see a supernova in our lifetime? Yes, and maybe even soon. There's a star called Betelgeuse, a red supergiant 640 light-years away. In 2019, it dimmed dramatically, sparking rumors of an imminent supernova. It hasn't exploded yet, but it will. Someday. When it does, it could shine as bright as the full moon, visible in daylight for weeks. Don't worry, it's too far to harm us. But it would be one of the most spectacular sky events in human history. From birth to death, stars shape the universe, and their final act is the most dramatic of all. Supernovas are not just endings, they are beginnings, forging the building blocks of life, lighting up the cosmos, and reminding us how small and how connected we truly are. The next time you look up at the night sky, remember, the atoms in your body were once part of a star that exploded billions of years ago. You are literally made of stars. Imagine a star more massive than our Sun, squeezed down into a sphere the size of a city, a place where gravity is so intense it warps the very fabric of space-time. We're talking about neutron stars, some of the most extreme and fascinating objects in the universe. These aren't your average celestial bodies. Neutron stars are the remnants of colossal supernova explosions, the incredibly dense cores left behind after a massive star collapses. Today we'll explore what makes neutron stars so mind-boggling, how they're formed, and the bizarre phenomena they create. We'll unravel the mysteries of objects that are essentially giant atomic nuclei held together by gravity. So what exactly is a neutron star? Well, picture this. Take the entire mass of our Sun, that's hundreds of thousands of Earths, and cram it into a sphere only about 12 miles, 20 kilometers across. That's roughly the size of a large city like Manhattan or San Francisco. This incredible compression results in densities that are almost unimaginable. A sugar cube's worth of neutron star material would weigh billions of tons here on Earth. It's so dense that the protons and electrons within atoms are crushed together, forming, you guessed it, neutrons. Essentially, a neutron star is one giant atomic nucleus, composed primarily of neutrons held together by its own immense gravity. The surface is incredibly smooth, likely smoother than a billiard ball, due to the intense gravitational forces evening out any irregularities. Now let's rewind and see how these cosmic oddities are born. It all starts with a massive star, much larger than our Sun. These titans burn through their nuclear fuel at a furious rate, eventually exhausting their supply. As the star runs out of fuel, the outward pressure from nuclear fusion that counteracts gravity weakens. The core collapses catastrophically under its own weight. This implosion triggers a supernova, one of the most energetic events in the universe. During the supernova, the outer layers of the star are blasted into space, enriching the surrounding interstellar medium with heavy elements. Meanwhile, the core continues to collapse. If the core's mass is between roughly 1.4 and 3 times the mass of our Sun, the so-called Tolman-Oppenheimer-Volkoff limit, gravity overcomes all other forces, squashing the core into a neutron star. If the core is too heavy, it becomes a black hole. But that's a story for another time. But the story doesn't end there. Newly formed neutron stars are often born spinning incredibly fast, sometimes rotating hundreds of times per second. This rapid rotation, combined with their intense magnetic fields, leads to some truly spectacular phenomena. These magnetic fields, trillions of times stronger than Earth's, channel beams of radiation out from the star's magnetic poles. As the star rotates, these beams sweep across space like a lighthouse beacon. If one of these beams happens to point towards Earth, we detect it as a pulsating signal. This is what we call a pulsar. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, and their regular pulses initially baffled astronomers. Some even jokingly considered the possibility of them being signals from extraterrestrial civilizations. Then there are magnetars, a special type of neutron star with even more extreme magnetic fields, thousands of times stronger than those of typical pulsars. Magnetars can unleash powerful bursts of X-rays and gamma rays, some of the most energetic events observed in the universe. These bursts can even disrupt Earth's atmosphere, despite originating from light years away. What's going on inside a neutron star? That's a question that continues to challenge physicists and astronomers. While we have theoretical models, directly observing the interior is, of course, impossible. Imagine peeling back the layers of an onion. The outermost layer, the crust, is a rigid layer of ions and electrons. Beneath the crust lies the outer core, a superfluid of neutrons. Further down, in the inner core, things get even weirder. Some theories propose that the immense pressure in the inner core could lead to the formation of exotic particles, like hyperons or even free quarks, the fundamental building blocks of matter. Understanding the composition of the inner core is a major goal of neutron star research, as it could provide crucial insights into the behavior of matter under extreme conditions, pushing the boundaries of our understanding of physics. Neutron stars aren't just interesting for their extreme densities and magnetic fields. They are also key players in the emerging field of gravitational wave astronomy. When two neutron stars orbit each other in a binary system, they gradually spiral inwards, emitting gravitational waves, ripples in the fabric of space-time. These gravitational waves can be detected by instruments like LIGO and Virgo, providing us with a completely new way to study these objects. In 2017, astronomers made history by detecting gravitational waves from the merger of two neutron stars. This event, known as GW 170817, was also observed across the electromagnetic spectrum, from radio waves to gamma rays, providing a wealth of information about neutron star mergers and the creation of heavy elements like gold and platinum. Speaking of heavy elements, neutron star mergers are now believed to be a primary source of many of the elements heavier than iron in the universe. During the merger, vast quantities of neutron-rich material are ejected into space. These neutrons are rapidly captured by atomic nuclei through a process called the R process, rapid neutron capture, leading to the formation of heavy elements. So, the gold in your jewelry might have been forged in the fiery collision of two neutron stars billions of years ago. Despite the incredible progress in understanding neutron stars, many mysteries remain. For example, what is the exact equation of state for matter at such extreme densities? How do magnetars generate such powerful magnetic fields? What exactly is happening in the inner core? Future observations with more powerful telescopes, both on Earth and in space, and continued gravitational wave detections will undoubtedly shed more light on these fascinating objects. You might be wondering, why should we care about these distant and exotic objects? The study of neutron stars helps us to understand fundamental aspects of physics, gravity, and the universe itself. They provide a unique laboratory for testing our theories of gravity, nuclear physics, and particle physics. And, as we've seen, they play a crucial role in the creation of the elements that make up our world, including the elements that make up us. So, the next time you look up at the night sky, remember that there are these incredible cosmic giants lurking out there, neutron stars, objects of immense density, powerful magnetic fields, and profound scientific importance. They are reminders of the extreme and wondrous nature of the universe we inhabit. Imagine a magnet so powerful it could rip apart atoms. a celestial object with a magnetic field stronger than anything you can possibly comprehend. We're talking about magnetars, the cosmic powerhouses that make every other magnet in the universe look like a fridge magnet. These aren't your average stars. Magnetars are a special type of neutron star, packing unimaginable density and an insane magnetic field into a space only a few miles wide. In this video, we'll delve into the bizarre world of magnetars, how they form, the unbelievable forces they unleash, and why scientists are so fascinated by these cosmic oddities. Buckle up, because this is going to be magnetic. To understand magnetars, we need to talk about stars. Specifically, the big ones. Stars much larger than our Sun eventually run out of fuel and collapse in on themselves in a spectacular supernova explosion. Depending on the star's size, what's left behind can be a black hole or a neutron star. Neutron stars are incredibly dense. Imagine squeezing the mass of the Sun into a sphere the size of a city. They also spin incredibly fast, sometimes hundreds of times per second. Now, imagine all this, plus a magnetic field that's trillions of times stronger than Earth's. That's a magnetar. To put it in perspective, a fridge magnet might have a magnetic field of about 0.01 Tesla. The Earth's magnetic field is about 0.00005 Tesla. A typical neutron star, maybe 1 to 100 Tesla. A magnetar? We're talking 100 million to 1 billion Tesla. That's strong enough to demagnetize your credit cards from halfway to the moon. Okay, maybe not, but you get the idea. So how do these cosmic magnets get their incredible power? The exact mechanisms are still a subject of intense research, but there are two leading theories. The first, and most widely accepted, is the dynamo theory. Inside a newly formed neutron star, there's a turbulent mix of super-hot, electrically conductive plasma. The rapid rotation of the star, combined with convection currents, think of boiling water, creates a powerful dynamo effect, like a giant generator amplifying the magnetic field. The second theory is the fossil field theory. This suggests that some stars are born with unusually strong magnetic fields already, and when they collapse into neutron stars, those fields get compressed and amplified to magnetar levels. The supernova itself also plays a crucial role in setting the stage for either of these processes. Now let's talk about what this immense magnetic field does. It's not just a number, it fundamentally changes the physics around the magnetar. The magnetic field is so strong that it can distort the shape of atoms, even bending them into long, thin needles. The surface of a magnetar is under immense stress, leading to what are called starquakes. These starquakes release tremendous amounts of energy in the form of X-rays and gamma rays. These flares can be incredibly powerful, and in rare cases, they've even been detected here on Earth. While not directly harmful, a large enough flare could potentially disrupt satellites and communication systems. Because magnetars primarily emit X-rays and gamma rays, scientists use specialized telescopes in space to detect and study them. Telescopes like Chandra, XMM, Newton, and Fermi are constantly scanning the skies for these high-energy emissions. One famous example is SGR 1900+14, a magnetar that produced a massive flare in 1998. Another is SGR-J 1550-5418, which is particularly active and has been studied extensively. Studying magnetars is a challenging task. They're incredibly distant, and their behavior can be unpredictable. But every observation brings us closer to understanding these extreme objects. Let's be clear, you really don't want to get close to a magnetar. If you were unfortunate enough to stray too near, the consequences would be, well, let's just say unpleasant. The immense tidal forces would stretch you out like spaghetti, a process scientists charmingly call spaghettification. The extreme radiation would fry you instantly, and the magnetic field, it would rip apart the very atoms that make you you. Thankfully, magnetars are located far, far away, so we don't have to worry about this happening anytime soon. But understanding their extreme effects helps us understand the fundamental laws of physics at their limits. So what's the point of studying these terrifying objects? Well, magnetars play a crucial role in the grand scheme of the universe. They're thought to be a source of heavy elements, forged in the supernova explosions that create them. They may also contribute to the overall magnetic field of the galaxy. Perhaps most intriguingly, magnetars are now suspected as a possible source of fast radio bursts, or FRBs, mysterious flashes of radio waves from distant galaxies that have baffled scientists for years. The study of magnetars is an ongoing and exciting field. New telescopes and space missions are being developed to probe these objects in greater detail. Scientists are working to unravel the mysteries of their formation, their internal structure, and the mechanisms behind their powerful flares. Understanding magnetars is crucial for understanding the fundamental physics of extreme environments. Magnetars, the universe's most powerful magnets. They are extreme objects that challenge our understanding of physics and offer a glimpse into the most violent and energetic processes in the cosmos. From their terrifying magnetic fields to their possible connection to fast radio bursts, magnetars continue to surprise and intrigue us. They remind us that the universe is full of wonders and that there's always more to discover. If you enjoyed this video and want to see more like it, then please consider hitting the like button and subscribing to the channel. Thanks for watching.